First of all, I want to thank the chairman of the European Working Group for inviting me at this workshop and for giving me the opportunity of sharing with you my experience on seismic analysis of earth dams. I will speak about earth dams, but since the workshop focus on the procedure for the selection of the input grid motion, I would to show you some of the results that our research units obtained in the framework of an Italian research project, which is the Red Reef project, which focuses on the assessment of the seismic risk of earth dams and embankments. And so I will show you two main aspects of our results. The first concern with the review of a large set of field data related to post-seismic surveys on earth dams. And the aims of this part of the presentation is to introduce some suitable performance indexes of the seismic performance of dams. And if I have enough time, in the second part of my presentation, I would like to show you some results of numeric analysis which are devoted to define some set of seismic parameters which are very well related to the crest settlement of earth dams, which is usually assumed as an index of the seismic performance of this kind of geotechnical systems. In the frame of the modern procedure for performance-based analysis of earth dams, usually we check the occurrence of a given ultimate of serviceability limit state for different seismic scenarios. So it's necessary to introduce in this kind of procedure some indexes that describes the seismic performance and that allow to check the occurrence of the selected limit states if this index is exceeded during the seismic motion during the seismic event. However, for earth dams, but I mean in general for dams, the selection of this kind of index is very difficult for several reasons. First of all, as you know, dams, but also earth dams are very complex engineering system, which seismic response is related to the seismic response of the foundation soil, of the foundation of the dam body, which is made of earth in my case. And the seismic response of the overall plant is also related to the behavior of many components and equipments which are very influent on the post-seismic serviceability condition and the post-seismic operative condition of the plants. So in the field of earth dams, usually we use a very practical approach. And according to the large set of data which are available in the literature, usually we use the crest settlement as a parameter, which is the main parameter related to the seismic performance of the dams. The crest settlement is very well related to the overall level of damage to the plant, and so it is usually adopted as a reliable index to check the seismic performance. So in this framework, my presentation, the first part of my presentation is devoted to show you a large set of data deriving from literature that we reviewed to define some threshold values of the crest settlement to be used as a performance index for checking the occurrence of limit states. And then we try to detect the main seismic parameters that are well related to the amplitude, to the magnitude of the crest settlements of earth dams. The data set that we use consists of about 145 case histories. And most of them concern with homogeneous or zoned earth dams. We have also a few data about hydraulic fill and tailing dams, but my presentation mainly concerned with earth dams, zoned or homogeneous earth dams. The database consists of about 145 case histories, which means combination of an earth dam and post-seismic surveys. The height of the dam range in a very large interval. We have dams from 15 meters to about 250 meters. The data concern with evaluation of the crest settlement that we analyzed as a function of the main seismic parameters, which are generally related to the magnitude or to the level of damage induced by an earthquake. So in this plot, you can see the plot of the crest settlement against the magnitude of the event. The data set consists of about 670 earthquakes, which occurred with magnitude from 4.5 to about 9, and the dams were located at epicentral distances which vary between 1 kilometers to about 300 kilometers. So in the site of interest for the dams, we might expect both near and far field effect, and the peak ground acceleration also vary in a very large interval. We have acceleration from 0.1 g to about 0.8 g for the most significant event. We use all the data available in the literature for this 145 case history to check the level of damage, and we re-examined and reclassified the damage into 4 levels, into 4 classes, which are consistent with the Italian seismic code on dams, but is also consistent with the ICOLD guidelines on earthquake effect on damage. So we introduced 4 classes of damage, which are described in the slide, and we re-examined all the data from geotechnical surveys to achieve a relationship between a given level of damage and a given level of crest settlements. And as is common in this kind of procedure, we normalize the crest settlement with respect to the overall height of the dam, which is the actual height of the dam and the height of the foundation soil underneath the dams. This is the distribution of the class of damage in our database. And first of all, I want to stress that most of the dams, of the earth dams that we analyze, performed very well. In most of the cases, no damage or minor level of damage were observed during the post-seismic surveys. Only in few cases, we note serious level of damage or some collapse, and in the last case, moderate level of damage. The plot in the below of my slide show you the distribution of the level of damage with magnitude and epicentral distance. And the first important aspect that I want to stress is that if you can see in the gray area, no level of damage, no damage were never observed in our database in the far field for magnitude less than 7.0. Conversely, large damage, serious damage, and some collapse were observed only in the near field for magnitude larger than about 6.7, and in the far field for magnitude in far field for magnitude greater than about 7.5. So this is the first important lesson from the analysis of this database. We try also to define some area of this plot to detect the possible occurrence of damage in earth dams. So I show you the first set of data, which is related only to the case of serious damage or collapse. The dashed red lines divide this plot in two areas. Above this line, we can detect the case of collapse. In the gray area, in the lower part of the diagrams, there are the case of no damage induced by earthquakes. In the middle area, which is green to yellow area, we have the cases of minor or moderate level of damage. So this kind of plot can be used for a preliminary check of the expected level of damage, depending on the site, the distance of the site of interest from the source, and depending on the magnitude of the expected seismic event. We try also to define a relationship between the level of damage and the amplitude of the crest settlement. So we divide all the data of the database in the 4 classes of damage which I have introduced in my previous slide. This plot clearly shows that for crest settlement lower than 0.1% of the overall height of the dam, no damage was never occurred in our database. So 0.1 could be assumed, according to Weiswood, as a reliable index for detecting the possible occurrence of some level of damage. The second plot shows you that in the case of minor level of damage, most of the data are bounded by a crest settlement level of equal to about 0.5 or 0.7%, which are again consistent with the data introduced by Weiswood, specifically 0.5 bound about the 80% of the data, while 0.7 bound about the 90% of the data. We have not enough data to define a proper index for the case of moderate, but we have enough data to define the upper level of damage, so the class of serious damage which generally occur for crest settlement greater than about 1% of the overall height of the dams. So the database could be used to define proper values, threshold values of the crest settlement, which can be used in performance-based design analysis of earth dams to check the occurrence of a given living state, or to check the occurrence of some class of damage defined according to our classification. In the second part of my presentation, I would like to show you some results of numerical analysis. This kind of analysis was devoted to check the possibility of introducing a set of seismic parameters that are well related to the amplitude of the crest settlements. And so the final aim is to link threshold values of the crest settlement to target values of these seismic parameters that can guide the selection of the input motion for dynamic analysis of earth dams. The results that I will show concern with a zoned earth dam. So is the San Pietro Dam, which was built in Italy, in the southern part of Italy, in a very high seismicity area. It was 48 meters high with a freeboard of about 2 meters. And we selected this case history because for this dam we have a lot of data deriving from site and laboratory investigation that allowed us to calibrate appropriate constitutive model for advanced dynamic analysis. The results that I will show concern with 2D plane strain finite element analysis carried out using a large set of input motion. We use about 58 records. I will show you the main characteristic of these records, but we select the records in order to have a large interval of variation of most of the main characteristics: peak acceleration, peak velocity, peak displacement, energy content, and frequency content of the input motion. The results of the numerical analysis were analyzed in terms of activation of plastic mechanism inside the body of the dam, dimension of the plastic mechanism, ground motion amplification inside the dam, and occurrence of vertical components of the ground motion due to the reflection of wave inside the body of the dam, occurrence of excess pressure in the soils of the dam and the foundation soils, and finally permanent displacement and deformation and corresponding value of the crest settlement. I will show you only the last two aspects of the analysis due to lack of time. So I will show you the relationship between the predicted crest settlement of the San Pietro Dam and a set of seismic parameters that we select to check the relationship between the crest settlement and these seismic parameters. First of all, I will show you some data about the case histories. This is the main cross section of the San Pietro Dam. The core is made by low plasticity clay silts. The shell is made by granular soil. The foundation soil consists of alluvial gravels, and they overlying a very stiff and deep flysch deposits. As I said, we have a lot of data derived from site investigation. In the right side of my presentation, you can see the data of the small strain shear modulus, which was evaluated starting from cross-solved data. In the left side, you can see some of the experimental data that we use to calibrate the constitutive model adopted in the numerical analysis. Let's go to some data about the input motion. As I said, we select 58 input motion. The input motion consists of horizontal acceleration records with peak values ranging from 0.15 G to about 0.7 G. But the main characteristic of the data set of input motion is the wide intervals of amplitude, energy, and frequency content that we select to obtain a very general results in terms of relationship between seismic parameters and crest settlement of the San Pietro dams. Okay, let's go to some results. This slide shows you the relationship between the crest settlement and some parameters describing the amplitude of the input motion in terms of acceleration, velocity, and displacement. In the lower part, you can see the relationship between the computed crest settlement and the strong motion duration and the equivalent loading of cycles, which generally are well related to the damage induced by cyclic action in soils and in geotechnical systems. As you can see, there is some clear trend, but none of these parameters can be assumed as a unique predictive variables due to the large dispersion of the data in each of the plots. So we try to detect the possible relationship between the settlement of the dams and some other seismic parameters. Specifically, we check the relationship between the settlement of the crest and some seismic intensity already available in the literature and widely used in the analysis, in the seismic analysis of both concrete and and earth dams. Specifically, in the upper part, you can see the relationship between the displacement, the permanent settlement of the crest, and their Riddle acceleration velocity displacement, the total intensity, which means something about the area's intensity. The only difference is a constant value. In the lower part, you can see the relationship between two other seismic intensities already available in the literature. It is clear that there is a better agreement between the crest settlement and the selected intensity measures, but none of them are suitable to predict in a very well the displacement of the computed displacement of the crest. So we try to detect some other parameters, some other combination of parameters which are well related to the crest settlement, and we found that a very well relationship can be found between the crest settlement and an intensity measure which is the product of the area's intensity and the mean period divided by the square root of the peak ground acceleration. As you can see, there is a very well relationship between the two variables, and so we decide to use this parameter to derive a predictive equation for the normalized crest settlements. In order to check the reliability of this predictive equation, we use some other data available in the literature. Specifically, we try to apply our relationship to the results by Elia and Ruania, which concern with the seismic response of the Marana Capaciotti, which is another homogeneous earth dam built in Italy, which have the same height of the San Pietro dams, but very different stiffness, and so very different frequency of vibration. Despite these very different characteristics of the dams, as you can see, the relationship that we propose and the intensity measure that we introduce seems to be very well related to the normalized crest settlements. So we decide to apply the relationship also to another Italian dams, is the Camastra dams, which has a higher height, about 57 meters, but a very low elastic period of vibration, which is about 0.3 seconds. Again, there is a very well relationship between the permanent displacement, the normalized permanent displacement, and the variable that we suggest as an intensity measure to predict the settlement of the dams. And so I will go to my conclusion, which is an empirical predictive equation to estimate the normalized crest settlements as a function of the main parameters, which are in our analysis seems to be better related to the level of damage induced by the earthquake. Specifically, the intensity measure accounts for energy content to the area's intensity, to the frequency content to the mean period, and to the amplitude of the input ground motion to the peak ground velocity. So the work is actually in progress. We want to check the reliability of this predictive equation with the other dams, with the other numerical results available in the literature, but this intensity measure seems to be very promising, and it could be used for both predictive purposes, but also to detect some target values of these seismic parameters that can guide the selection of the input motion for dynamic analysis of earth dams. Okay, I have completed, and I want to thank you for your kind attention.